The cosmic story that unfolded following the Big Bang is ubiquitous no matter where you are. The formation of atomic nuclei, atoms, stars, galaxies, planets, complex molecules, and eventually life is a part of the shared history of everyone and everything in the universe. Even though all of these things likely arise at somewhat different times at different locations in the universe, largely dependent on the initial conditions such as temperature and density, once enough time goes by, they're found literally everywhere. At least once, here on Earth, life began at some point in the universe. Scientists believe that life has found a home on Earth for around 4 billion years, and that's a significant fraction of the universe's 13.77 billion year history. But if life arose here, presumably, it could have appeared anywhere. In other words, life may be much, much older than Earth. It may have arisen in our solar system before Earth even finished forming. And for sufficiently broad definitions of life, it might even be possible for life to have appeared mere seconds after the Big Bang. Interestingly, this assumption is supported by data obtained by our most powerful space observatory, the James Webb Telescope. New findings from James Webb just reveal that the essential elements for life were present much earlier than previously believed. In other words, life as we know could have existed much earlier than previously thought. But does it hold true? Join us as we dig deep into how James Webb could upend our understanding of the origin of life. To explore the origins of life, first, we have to define it. There are over 200 published definitions of the term, which shows just how difficult this concept is to grapple with. For example, are viruses alive? They replicate but need a host to do so. What about prions, the pathogenic protein structures? Debates continue to swirl over the line between life and non-life. But for our purposes, we can use an extremely broad but very useful definition. Life is everything that's subject to Darwinian evolution. This definition is handy because we'll be exploring the origins of life itself, which, by definition, will blur the boundaries between life and non-life. At one point, deep in the past, Earth was not alive. Then it was. This means that there was a transition period that will naturally stretch the limits of any definition you can muster. Plus, as we dig deeper into the past and explore other potential options for life, we want to keep our definition broad, especially as we explore the more extreme and exotic corners of the universe. With this definition in hand, life on Earth arose at least 3.7 billion years ago. By then, microscopic organisms had already become sophisticated enough to leave behind traces of their activities that persist to the present day. Those organisms were a lot like modern ones. They used DNA to store information, RNA to transcribe that information into proteins, and the proteins to interact with the environment and make copies of the DNA. This three-way combo allows those batches of chemicals to experience Darwinian evolution. But those microbes didn't just fall out of the sky. They evolved from something. And if life is anything that evolves, then there had to be a simpler version of life appearing even earlier in Earth's past. Some theories speculate that the first self-replicating molecules, and hence the simplest possible form of life on Earth, could have arisen as soon as the oceans cooled, well over 4 billion years ago. And Earth may not have been alone. Mars and Venus had similar conditions at that time, so if life happened here, it may have happened there too. But the Sun was not the first star to ignite into fusion. It is a product of a long line of previous generations of stars. Life as we know it requires a few key elements: hydrogen, oxygen, carbon, nitrogen, and phosphorus. With the exception of hydrogen, which appeared in the first few minutes after the Big Bang, all of these elements are created in the hearts of stars during their life cycles. So, As long as you have at least 1 or 2 generations of stars living and dying, and thereby spreading their elements out into the wider galaxy, you can have Earth-like life appearing in the universe. This pushes the clock back on the possible first appearance of life to well over 13 billion years ago. This era in the history of the universe is known as the cosmic dawn, when the first stars formed. Astronomers aren't exactly sure when this transformative epoch took place, but it was somewhere within a few hundred million years after the Big Bang. As soon as those stars appeared, they could have started creating the necessary elements for life. This has even been confirmed, thanks to new findings made by the James Webb Space Telescope. Scientists used James Webb's data to measure the oxygen in 138 galaxies that existed in the first 2 billion years of the universe. The team found that most of the galaxies had oxygen abundances similar to modern galaxies. But out of the 7 earliest galaxies in the sample, those that existed when the universe was only 500 to 700 million years old, 6 of them had roughly half the predicted oxygen content. This rapid increase in oxygen content occurred earlier than astronomers were expecting. This opens the possibility that with the necessary ingredients like oxygen already readily available in the early universe, life as we know it, built on chains of carbon using oxygen to transport energy and submersed in a bath of liquid water, may have appeared sooner than previously thought. Even other hypothesized forms of life based on exotic biochemistries require a similar mixture of elements. For example, some alien life may use silicon instead of carbon as a basic building block, or use methane instead of water as a solvent. No matter what, those elements have to come from somewhere, and that somewhere is in the cores of stars. Without stars, you can't have chemical-based life. But perhaps it's possible to have life without chemistry. It's hard to imagine what these creatures might be like. But if we take our broad definition, that life is anything subject to evolution, then we don't need chemicals to make it happen. Sure, chemistry is a convenient way to store information, extract energy, and interact with the environment, but there are other hypothetical pathways. For example, 95% of the energy contents of the universe are unknown to physics, literally sitting outside the known elements. Scientists aren't sure what these mysterious components of the universe, known as dark matter and dark energy, are made of. Perhaps there are additional forces of nature that work only on dark matter and dark energy. Maybe there are multiple species of dark matter, an entire dark matter periodic table. Who knows what interactions and what dark chemistry play out in the vast expanses between the stars. Hypothetical dark life may have appeared in the extremely early universe, well before the emergence of the first stars, powered and mediated by forces we do not yet understand. The possibilities can get even weirder. Some physicists have hypothesized that in the earliest moments of the Big Bang, the forces of nature were so extreme and so exotic that they could have supported the growth of complex structures. For example, these structures could have been cosmic strings, which are folds in space-time anchored by magnetic monopoles. With sufficient complexity, these structures could have stored information. There would have been plenty of energy to go around, and those structures could have self-replicated, enabling Darwinian evolution. Any creatures existing in those conditions would have lived and died in the blink of an eye, their entire history lasting less than a second. But to them, it would have been a lifetime. What's more, it has recently been shown that if you have nucleobases in an aqueous environment, things like RNA, DNA, or even PNA, peptide nucleic acids, that these nucleotides will line up along the various amino acids in a peptide chain. If they can pair up with their conjugate base, or peel off and draw additional amino acids onto them, they can effectively reproduce to a high degree of accuracy the original peptide chain. This scenario, known as RNA peptide coevolution, is how most working scientists investigating the origin of life now believe that self-replication, built on the backbone of metabolic processes, first came about. Although not every biologist agrees that. A free-floating molecule that can metabolize resources and replicate itself rises to the threshold of being life rather than non-life. This likely represents the first concrete steps that led from simple chemical processes to biological ones. These primitive metabolizing replicators likely came into existence alongside one another, possessing a great diversity among them, with many, if not most, of them certainly going extinct along the way. This predates a universal common ancestor on Earth, and even our notion of what a cell is by many hundreds of millions, and maybe over 1 billion, years. Nonetheless, this is where current scientific thought takes us as to how life first originated on Earth. Because we have every reason to believe that the laws and ingredients we have on Earth are found all over the universe, it makes sense to look for those same fingerprints, wherever we're capable of looking. In space, whether around the centers of galaxies or around massive, newly forming stars, or even in the environments where metal-rich gas is going to form future stars, we find a whole host of complex organic molecules. These range from sugars to amino acids to ethyl formate, the molecule that gives raspberries their scent, to intricate aromatic hydrocarbons. That is, molecules that are thought to be precursors to life. So far, we've only found these molecular biohints nearby, of course, but that's because we don't know how to look for individual molecular signatures in environments that lie well beyond our own galaxy. However, as we look to greater and greater distances, we do indeed find that there are galaxies and portions of even very early galaxies that have the right populations of stars and the right metallicities to them, to be excellent candidates for life to arise within them. In the most extreme cases, we find locations from within the first 1 to 2 billion years after the Big Bang that might potentially be home to life already. In short, perhaps a colder, smaller planet, like Mars, a warmer, more energetic planet, like Venus, a world with liquid methane rather than water, oceans like Titan, a frozen world with a subsurface ocean, like Enceladus or Triton or Pluto, or a water-rich world that experiences significant tidal heating like Europa, could provide an environment where life can arise, survive, and thrive as well. Quite possibly, there may even be environments out there that are more conducive to the origin of life than even early Earth was. Perhaps a planet or moon around a K-type or M-type star, both smaller, redder, and longer-lived than our Sun, would do the job? Perhaps a planet where life arises and then gets struck by a large object, like an asteroid, would seed other planets, moons, and even other star systems with that life. And perhaps, quite simply, if we rewound the clock to 4.5 billion years ago and made 1,000,000 identical copies of Earth, we could imagine how many of them would develop life. Would it be all 1,000,000 of them? A few thousand of them? Hundreds? Dozens? Just one? Or could life arising be such a rare occurrence that Earth is the outlier, that even in 1,000,000 identical early Earths, not a single one would develop life? This is the fundamental problem facing us. We are, in a very real sense of the word, the winners of a cosmic lottery. Despite all of the opportunities for failure at who knows how many critical stages, life arose, survived, and thrived on our planet. An unbroken chain for some 4 billion years. We know that we won the lottery, but we don't know what occurred to lead to our victory. We still don't know how life in the universe got its start, including whether life as we know it is common, rare, or a once-in-a-universe proposition. But we can be certain that life came about in our cosmos at least once, and that it was built out of the heavy elements made from previous generations of stars. If we look at how stars theoretically form in young star clusters and early galaxies, we could reach that abundance threshold after several 100 million years. All that remains is putting those atoms together in a favorable to life arrangement. If the universe forms the molecules necessary for life and then puts them in an environment conducive to life arising from non-life, like on a water-rich rocky planet, suddenly the emergence of biology could have come when the universe was just a few % of its current age. The earliest life in the universe, we must conclude, could have been possible during even the first 1 or 2 billion years after the hot Big Bang began. Once enough stars live and die, the material from their corpses gets incorporated into new stars, new molecules, and even new planets. Get enough of this enriched material together under the right conditions, and that's perhaps all it takes to result in life's all but guaranteed arrival. Back to the origin of life on Earth began more than 3 billion years ago, which evolved from the most basic of microbes into a dazzling array of complexity over time. But how did the first organisms on the only known home to life in the universe develop from the primordial soup? Frankly, science remains undecided and conflicted as to the exact origin of life, also known as abiogenesis. But we have some of the many different scientific theories on the origin of life on Earth. It started with an electric spark. Lightning may have provided the spark needed for life to begin. Electric sparks can generate amino acids and sugars from an atmosphere loaded with water, methane, ammonia, and hydrogen, as was shown in the famous Miller-Urey experiment in 1952. The experiment's findings suggested that lightning might have helped create the key building blocks of life on Earth in its early days. Over millions of years, larger and more complex molecules could form. Although research since then has revealed the early atmosphere of Earth was actually hydrogen-poor, scientists have suggested that volcanic clouds in the early atmosphere might have held methane, ammonia, and hydrogen, and been filled with lightning as well. Molecules of life met on clay. The first molecules of life might have met on clay according to an idea elaborated by organic chemist Alexander Graham Cairns-Smith at the University of Glasgow in Scotland. Cairns-Smith proposed in his 1985 controversial book, 7 Clues to the Origin of Life, that clay crystals preserve their structure as they grow and stick together, to form areas exposed to different environments and trap other molecules along the way and organize them into patterns, much like our genes do now. The main role of DNA is to store information on how other molecules should be arranged. Genetic sequences in DNA are essentially instructions on how amino acids should be arranged in proteins. Cairns-Smith suggests that mineral crystals in clay could have arranged organic molecules into organized patterns. After a while, organic molecules took over this job and organized themselves. Although Cairns-Smith's theory certainly gave scientists food for thought in the 1980s, it has still not been widely accepted by the scientific community. Life began at deep sea vents. According to the journal Nature Reviews Microbiology, the deep-sea vent theory suggests that life may have begun at submarine hydrothermal vents spewing elements key to life, such as carbon and hydrogen. Hydrothermal vents can be found in the darkest depths of the ocean floors, typically on diverging continental plates. These vents erupt fluid which is superheated by the Earth's core as it passes up through the crust, before being ejected at the vents. During its journey through the crust, it collects dissolved gases and minerals, such as carbon and hydrogen. Their rocky nooks could then have concentrated these molecules together and provided mineral catalysts for critical reactions. Even now, these vents, rich in chemical and thermal energy, sustain vibrant ecosystems. Abiogenesis by way of hydrothermal vents continues to be investigated as a plausible cause of life on Earth. In 2019, scientists at University College London successfully created protocells, non-living structures that help scientists understand the origins of life, under similar hot, alkaline environmental conditions to hydrothermal vents. life had a chilly start. Ice might have covered the oceans 3 billion years ago and facilitated the birth of life. And according to Jeffrey Bada at the University of California, key organic compounds thought to be important in the origin of life are more stable at lower temperatures. At normal temperatures, these compounds, such as simple sets of amino acids, are sparsely populated in water, but when frozen, become concentrated and facilitate the emergence of life, according to Bada's work published in the journal Icarus. Ice also might have protected fragile organic compounds in the water below from ultraviolet light and destruction from cosmic impacts. The cold might have also helped these molecules to survive longer, enabling key reactions to happen. The answer lies in understanding DNA formation. Nowadays, DNA needs proteins in order to form, and proteins require DNA to form, so how could these have formed without each other? The answer may be RNA, which can store information like DNA, serve as an enzyme like proteins, and help create both DNA and proteins according to the journal Molecular Biology of the Cell. Later, DNA and proteins succeeded this RNA world because they are more efficient. RNA still exists and performs several functions in organisms, including acting as an on-off switch for some genes. The question still remains how RNA got here in the first place. Some scientists think the molecule could have spontaneously arisen on Earth, while others say that was very unlikely to have happened. Life had simple beginnings. Instead of developing from complex molecules such as RNA, life might have begun with smaller molecules interacting with each other in cycles of reactions. These might have been contained in simple capsules akin to cell membranes, and over time more complex molecules that performed these reactions better than the smaller ones could have evolved scenarios dubbed metabolism-first models, as opposed to the gene-first model of the RNA world hypothesis. Life was brought here from elsewhere in space. Perhaps life did not begin on Earth at all, but was brought here from elsewhere in space, a notion known as panspermia. For instance, rocks regularly get blasted off Mars by cosmic impacts, and a number of Martian meteorites have been found on Earth that some researchers have controversially suggested brought microbes over here, potentially making us all Martians originally. Other scientists have even suggested that life might have hitchhiked on comets from other star systems. However, even if this concept were true, the question of how life began on Earth would then only change to how life began elsewhere in space. After all, perhaps somewhere, under some conditions we might even consider too exotic for life, there are living creatures completely unlike us, better suited to surviving, thriving, and building an interstellar civilization in the cosmos. Perhaps they're not made out of familiar ingredients like proteins, but something else entirely, like a crystalline or metallic set of structures. Despite the fact that we haven't received any positive signals from SETI, that we haven't found robust evidence for life on other worlds in our solar system, or detected any inhabited planets around other stars just yet, we have every reason to keep searching. After all, absence of evidence is not evidence of absence, and we have no right to expect that life, of any type or complexity, is going to be easy to find. But it is possible, and it occurred at least once. If we can find a second example, we'll have every reason to expect that the universe really is teeming with life. At that point, it simply becomes a numbers game. What are the odds, and what are the various prizes for winning? That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.